So in this screencast, we're going to be talking about the drawing of Lewis structures. What is a Lewis structure? A Lewis structure is basically a very detailed skeletal structure. Basically what we're going to be drawing is the skeletal structure with all of the electrons connected. So before we can actually talk about Lewis structures, we need to talk about skeletal structures. Kind of go take a step back. Now if you recall, a skeletal structure is basically actually drawing the molecules and saying this atom is bonded to this atom, is bonded to this atom, and it's very, very detailed and usually takes up a lot of space. That's why we try to avoid it. But sometimes we really need to know exactly where all the electrons are because it's going to dictate molecular geometry, it's going to dictate reactivity. So before we can draw Lewis structures, we have to go back and talk about skeletal structures. Basically, how are the atoms actually connected? So there are some general rules regarding skeletal structures. We're basically going with the, okay, given a molecular formula, got this many hydrogens, this many carbons, this many oxygens, I have to figure out how are they connected. And that's something you're going to have to, for the most part, be able to predict. The molecules we're going to be drawing in this course are relatively simple, they're not very big, and follow, for the most part, these general rules. So the first general rule is that hydrogen is always terminal, meaning it's always on the end. There's only one bond. Halogens are also always terminal, or usually terminal. So for example, water has this molecular geometry because hydrogen only wants to have one extra electron, so it only likes to make one bond. So if when I write H2O, even though I write H2 and O, and you might want to think that it's HHO, well it can't be because then this hydrogen sort of violating the octet rule because it's violating the duet rule because it's got 2 electrons over there and 2 electrons over there. And so that just doesn't make any sense. So hydrogen's always on the end. Halogens are also usually terminal for the same reason, because when we think about fluorine, it's got 7 valence electrons. And so it really wants to just make one more bond and loop that one more electron with some other species to form a single bond. So halogens, fluorine, chlorine, bromine, they're usually terminal. Second general rule is that the smallest electronegativity atom is usually the central atom. So for example, carbon, oxygen, this COCl2. Of these 4 elements, if we go back and remember our rules for electronegativity, you'll remember that carbon is the least electronegative element. And so this is actually the connectivity. So carbon is in the middle, bonded to chlorines, which are their terminal, and there's the oxygen. This is not the Lewis structure of COCl2. This is the skeletal structure. We haven't talked about, this is sort of like our first step. The first step to be drawing these Lewis structures is come up with this skeletal structure, and then we're going to add the rest of the electrons. The third general rule is that polyatomic species, so when we start adding more and more elements, are usually compact, meaning they're not really big, long chains. So for example, this compound, which, I don't remember the name of it. It's got a silly name. This is actually the skeletal structure where the sulfur, the lowest electronegativity element, is in the center, bonded to 2 fluorines and bonded to 2 oxygens. It's not actually this connectivity in a big long chain. Okay. One more thing before we actually talk about the drawing of Lewis structures. For my course, these general rules are sort of cast in stone. If I ask you to draw the Lewis structure of a compound and one of these 3 rules is sort of, violated, if you will, I will make sure that you know it. So I'm not going to sort of trick you and say, oh, well, yeah, this is one of the cases where the general rules didn't work. If the lowest electronegativity element is not the central atom, I will let you know, and I will specifically say, oh, in this compound, this is the central atom. So I'm never going to try to trick you. So the steps for drawing of Lewis structures is actually relatively straightforward if you follow this idiot-proof guide to drawing Lewis structures. This is a procedure for how to come up with the correct Lewis structure. This is not how atoms actually come together and bond. This is just a straightforward 5-step process for drawing the correct Lewis structure for a particular compound. I'm going to go through these relatively quickly and then we're going to do some examples quick. So the first thing we have to do is calculate the total number of valence electrons. The reason why we do the total number of valence electrons is because the valence electrons are the only ones we're actually going to draw, because we don't care about the core electrons because they never react. The valence electrons, recall, are the electrons that actually do something. They bond. So in our molecular structure, in our Lewis structure, we're basically drawing a skeletal structure and showing every single solitary valence electron in the system. So we have to know how many we're playing with. Step 1. 2, draw the skeletal structure and connect bonded atoms using a dash to represent each pair of electrons. So give everybody essentially a single bond. That's what we're doing in the beginning, sort of starting there. Some of them are going to be doubles, some are going to be triples, but we start with give everybody a single bond because we know there's at least one between them all. If we have any remaining electrons from our pile of valence electrons, we add them around the outer atoms first, give them all an octet, with obviously the exception of hydrogen because it only gets 2. 4, if we have any remaining electrons, we put them on the central atom. 5, if the central atom has less than 8 electrons, so it doesn't have an octet, we complete its octet by using non-bonding pairs of electrons from the outer atoms to form multiple bonds. Now, the key is you start with step 1, then go to step 2, then go to step 3, then go to step 4, and then go to step 5. The order is extremely important. And if, as soon as you see how it says, place remaining electrons, place remaining electrons. If you don't have any remaining electrons, you skip that step. If you don't have any remaining electrons, you skip that step. And if you follow this rule in its entirety, you'll get the correct Lewis structure. So now that we have those rules, and they're in your notes, so you can go back to them while you're going through the screencast, let us talk about a couple. So carbon tetrafluoride, which is CF4, has a total of 32 valence electrons. So carbon has 4, each fluorine has 7. You total that all up, we have 32 electrons from all the valence electrons from all 5 atoms in there that we have to play with. So the first step we've accomplished, that's 32 electrons. The next step is to draw the skeletal structure, carbon being the lowest electronegativity element of the 2. It's in the center, it likes to have 4 bonds, and there is our structure. So we already have 2, 4, 6, 8 electrons drawn. We still have 32. Okay, so we have remaining electrons. So we go to step 3, which says place remaining electrons around the outer atoms. There they are. Now, you can sit there and count up how many electrons you've drawn, giving everybody an octet, or you can sort of like, what I do to make it go a little bit faster, is I look and I say, okay, when I'm counting, because there's going to be times when you have to count how many electrons have I drawn, is I sort of like, I kind of look at this one fluorine, and this one fluorine has 8 electrons around it. This fluorine has 8 electrons around it. This fluorine has 8 electrons around it. This fluorine has 8 electrons around it. And 8 times 4 is 32. So I'm done. I'm out of valence electrons. Step 4 says place remaining electrons on the central atom. I don't have any. I'm done. Step 5, if the central atom has less than 8 electrons, make a multiple bond, blah, blah, blah. And the central atom, the carbon, oh, look at that. It's got 8 electrons. Its octet is satisfied. Outer atoms, octet satisfied. Central atom, octet satisfied. Done. That's the Lewis structure. That is the Lewis structure for carbon tetrafluoride. Next, compound that's known as acetone, H2CO. First step, calculating total number of valence electrons. So oxygen has 6, carbon has 4, each hydrogen has 1, for a total of 12 valence electrons. Step 2, draw a skeletal structure. Now, obviously, hydrogen can't be the central atom. Oxygen is more electronegative than carbon, so carbon's probably the center. So, and there's my compact structure. Carbon in the middle, terminal hydrogens, oxygen. So I have accounted for 2, 4, 6 electrons I've drawn. Next step is place remaining electrons around the outer atoms, give each an octet. We ignore hydrogen, we go to oxygen. It's only got 2 electrons around it, so we put 6 more. And we have run into our limit. We have drawn 2, 4, 6, 8, 10, 12 electrons. So we're out of electrons. Step 4 says place remaining electrons on the central atom. Don't have any more electrons. Skip step 4. Step 5, if the central atom, in this case the carbon, has fewer than 8 electrons, we need to form multiple bonds by taking lone electrons from outer atoms. So there's a lone, what we're going to do is we're going to take one of these lone pairs, and don't worry about which one it is, they just represent pairs of electrons. One of these lone pairs, remember, a bond is actually a pair of electrons. So we're going to take one of these pairs of electrons and we're going to form a multiple bond. Now, what does that do? The oxygen still has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. The oxygen still has 8 electrons around it, but now the carbon also has 8 electrons around it. Everybody has an octet. I've used the correct number of electrons. There is my most stable Lewis structure. In this case, it's got a double bond. Again, let me emphasize, this is not how molecules actually do this bonding. When carbon and hydrogen and oxygen come together to form this molecule, the carbon and oxygen don't make a single bond and then sit there and debate about it, just like, oh, I don't have enough electrons. Let me take this lone pair and make a double bond. No, it doesn't happen that way. We are following a nice stepwise process for coming up with the most stable Lewis structure. It's not the way that Mother Nature actually builds these things. It's how do we get to the same final answer? So always remember that. Hydrogen cyanide. Formula for hydrogen cyanide is HCN. So 1 nitrogen, 1 carbon, 1 hydrogen gives me a total of 10 valence electrons. 6 from the oxygen, 4, 3. Total of 10 of valence electrons. Sorry, there's no oxygen. 5 from the nitrogen, 4 from the carbon, 1 from the hydrogen. That's where I get 10. Where did I get the oxygen? I don't know. I wasn't thinking. I apologize. 10 valence electrons. So there's my skeletal structure. Carbon, lower electronegativity of all the species. Hydrogen on the end, nitrogen on the end. I've drawn 4 electrons. 1, 2, 3, 4. That means I have 6 left. Step 3 says place remaining electrons around the outer atoms to give them all an octet. So nitrogen is 6 electrons short. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've drawn all of my 10 electrons. I am out of electrons, so I ignore step 4. No problem. I move on. Step 5. If the central atom has fewer than 8 electrons, this carbon has fewer than 8 electrons. It's only got 1, 2, 3, 4. So you have to make multiple bonds. The only source for multiple bonds are the nitrogen. 1, 2, 3, 4. And so this nitrogen, 2 of those disappear and turn into what is known as a triple bond. Nitrogen still has 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. Now the carbon also has 8. Last example, HOCl. 7 valence electrons, 6 valence electrons, 1 valence electron gives me a total of 14. Oxygen actually has a lower electronegativity than chlorine. The other thing that we know is that chlorine is usually terminal, hydrogen is usually terminal, so the oxygen's in the middle. 14 valence electrons, we've drawn 4, so we go with the chlorine first, give her 8, so now chlorine has 8, and we have 2, 4, 6, 8, 10 electrons shown, which means we have 4 left, because we have a total of 14. Step 4 says put them on the central atom. There we go. Step 5 is moot, because the central atom has 1, 2, 3, 4, 5, 6, 7, 8. So there's the correct Lewis structure for HOCl. And it just gets harder from here, but there's the basic 5-step process.